Alright folks, we're back. So far we've been doing local extrema and local minimum. Now I would like to talk about absolute maxima and absolute minima. So if we're talking about absolute extrema, okay, we could have absolute extrema at local extrema, or they could be at the boundaries. The boundaries is if f of xy is defined on a closed region. Okay, so if you have a continuous differentiable function, right, we know from Calc 1 it's going to have absolute maxima, absolute minima definitely on a closed region. Okay, so we might have problems where the function is defined on a closed region and we're interested in the absolute. That means the biggest guy on the block, okay, or the smallest guy on the block. So where can I find those? Where I can find those at the local extreme, or I can find them on the boundaries. To illustrate this point, I'd like to do the following question. Let's take as an example, let f of xy be defined as x squared minus y squared minus 2x plus 4y. Okay, but now this function has as domain, of course everything is legal here, you can put any x and y you'd like, but let's limit the region be defined. Let's define it on the region R. And what is the region R? Bounded below, bounded on the bottom, bounded below by the x-axis. Okay, bounded above bounded above by the line y equals x plus 2, and on the right by the line x equals 2. Okay, so the first order of business, we're limiting the domain of this function. Let's try to draw the domain on the xy plane. Okay, on the xy plane. So it says it's bounded below by the x-axis, then it's bounded above by the line y equals 2. So of course y equals 2 is going to go through minus 2 and 2, right? So it's going to be this line. Okay, this line. So we have this, and then we have the line x equals 2. So here is x equals 2. So that would be this vertical line. Okay, so the region I'm talking about is this triangular region. This is a region where the function is defined as. So for each point in this region, right, it's going to give me, the function just gives me a height. Okay, now this function is defined also outside this region, but I'm only considering it for this region in this problem, okay, specifically this region. We want the absolute extrema points, the absolute maximum and absolute minimum on this region, okay? Now, if the points are inside the region, properly interior points, then they are going to be local extrema and local maxima or local minima, so I can find them by setting the derivative equal to 0. On the boundaries, I'll have to be really careful. This is more difficult than the single variable thing. On the single variable, the boundaries are always 2 endpoints, so you just plug in 2 points. Here, we're actually going to do some work, so I'll try to take it step by step and show it to you in detail. First of all, let's look at the partials. So if we look at the partial f sub x, what is the partial f sub x? That's going to be 2x, okay, and minus 2, and that's it. And the partial f sub y is going to be minus 2y plus 4, and that's it. Okay. So now let me move this up a little bit. So we have the action going on in the center. So f of x, f sub x equals 0, of course implies 2x minus 2 equals 0, okay? And from here, I get that x is equal to 1. F sub y equals 0 is going to imply that minus 2y plus 4 is going to equal to 0. And here, from here, I'll get that y is equal to 2, okay? So we have this point 0, so sorry, we have the point 1, 2, okay? The question is, where is this point 1, 2? Is it an interior point, okay? Or is it, first of all, inside our region? Maybe it's outside our region. Now, the x-coordinate is 1, so that's the x-coordinate. And the y-coordinate is 2, so that's the y-coordinate somewhere. Remember, this line itself was y equals x plus 2, okay? So the value of the line at 2 would be 4. Since I'm at 1, 2, we're talking about some point over here. It's inside the region. Again, I just looked at the y value the line achieves at x equals 2. That would be 2 plus 2 equals 4. And so it's below that, so I'm well inside the region here. Okay, this point is 1. So it's 1, 2 is over there somewhere. Okay, it's actually, sorry, I drew it wrong. It's exactly here at this point. Okay. All right, so it's an interior region. Now, you might think, hey, I gotta do the second derivative test. I need to look at second derivatives. We don't need to, because we're looking at the absolute extrema. We can just find these values and compare with any other values we find. Okay, we know the function is continuous. It's gonna achieve, it's gonna achieve its absolute absolute maximum and absolute minimum on a closed interval. So you just look at you will just compare values, okay? So what do we have? The value of the function at 1, 2 is 1, 2, and the z value is, let's go up here, plug in 1, 2, we get 1 minus 4, that's a minus 3, minus a 5, plus an 8, so that's going to be a 3, okay? So this is one of these points that I'll care about. Okay, now that's the only interior point we have. So now next we need to consider the boundary. Next we consider the boundary. Okay, so let me give some points here. Let me give it some points here. I'll call this point here A. I'll call this point here B. And I'll call this point here C. Okay. So we have, it's not just these 3 points. Actually, the boundary is made up of these 3 lines now, right? There's this one line, there's this line, and there's this line, okay? So I have to consider all these lines. So on the line segment, so let's do number 1. So number 1, on the line segment AB, AB. Okay, so let's do this carefully. So we're on this line segment AB, which means here we have y equals x plus 2. Okay, x plus 2. So that means f of x y is gonna turn into f of x plus 2. So wherever I see a y, this is gonna be my y now. Okay. Wherever I see a y, I'm going to plug in x plus 2. But what was the formula for f of x? Let's go back here. The formula for f of x, if you remember, was x squared minus y squared minus 2x plus 4y. Sorry, my camera is falling again. Let me try to fix that. Okay. So if we plug in this value here, well, what are we going to get? X squared minus y squared is going to be x plus 2 squared, okay? Minus 2x, don't mess with that, plus 4, well, what is y? That's x plus 2, okay? So if I simplify that, let's do some math. Sorry, you didn't see that. I just plugged it in. I'm sorry. I keep doing this, don't I? Okay. So I just plugged in wherever I saw an x, the formula was x squared minus y squared minus 2x plus 4y. So I just plugged in an x plus 2 wherever I saw y. So now let's try to simplify this guy. We're going to have an x squared minus an x squared when we open this up. There's going to be a 4x, so that's going to be a minus 4x, a minus 4, another minus 2x. All right, so far so good. Plus a 4x plus an 8. Okay, so now we have these guys. Well, they're gone. So this is going to be minus 6x plus 4x. That's going to be minus 2x. And then this is going to be a 4. So minus 4 plus 8. So we have minus 2x plus a 4. Okay. So this is very interesting. This function we have is this function. If we just summarize it, it turned into this function on the line y equals x plus 2. Okay. And well, we said that's equal to this function. Notice on this line here on x plus 2, whatever the shape here on top is, we don't know. But when we cut it down parallel to this, when we cut it down like this, okay, we're going to get a curve. On the surface, we're going to find the curve. And which curve we're going to find? Well, it's not a curve. We find the line basically, okay? This line minus 2x plus 4. So the question is, this is now down to single variable calculus. Well, where can I have this guy? Where can this guy be a minimum? Well, where can it be a minimum? Well, let's do f prime of x plus 2, okay, with respect to x, of course. Well, that's just minus 2. It's never equal to 0, okay? So you cannot have, this behaves like the interior of a single variable function, okay? Like the interior, you cannot have, because it's a minus 2, there are no points, no candidates, okay? No points from here, because the derivative is never equal to 0. Okay, but you're going to say, hold on, you forgot the endpoints. I'll do the 3 endpoints way at the end, okay? I'll do the 3 endpoints way at the end. Now, let's look at the line segment. Let's look at the line segment BC. Let me go clockwise. Number 2, let's look at the line segment BC. On line segment BC. Okay, so there, remember there, this line segment is this is x equals 2. Okay, this is the line x equals 2. So f of xy is just, it's actually again a function of single variable. It's just f of 2y. Okay, so let's just plug in everything here. Remember the function was x squared minus y squared minus 2x plus 4y. So if I plug in 2 to here, x squared is going to be 4 minus y squared, don't mess with it, minus 2 times 2, that's going to be another 4, plus 4y. Okay, so these guys are going to cancel, and we are going to have minus y squared plus 4y. Okay, so if we can finish it here, then f prime of 2y, with respect to y of course, is going to be what? It's going to be minus 2y plus 4. And when will this be equal to 0? This is going to be equal, let's go on to the next page actually. It's too crowded here. Let's go on to the next page. Okay, so I'll keep them together like this so you can see it. So f prime equals 0 here, it's going to imply y is equal to 2. Okay, but y equals 2, what's the x coordinate? Hey, we're on the line x equals 2, so the x coordinate is also 2, right? Since we are on x equals 2, on the line x equals 2, we are on x equals 2. We have the coordinate 2, 2, and let's calculate the y value there. The z value. So remember the function was x squared minus y squared. Well, that's going to be a big fat 0. Minus 2 plus 8, that's going to be a 4. Okay. So we have 2, 2, 4 as another candidate, okay, as another candidate. Now again, if we let me redraw the region here, so we have it in front of us, right in front of us. The region was like this, okay. The region was like this, remember? Okay, this was -2. This point here, -2. This was 2. This was the line y equals x plus 2. And this was the line y equals 2. So sorry, not y equals 2, x equals 2. X equals 2, sorry, my bad. And this is the x-axis. So, alright, and I labeled the points. This was A, this was B, this was C. Okay? So now we're checking the boundary again. The only line segment that's left, and the function, let's write the function here again. We don't have to look at f of xy was equal to x squared minus y squared minus 2x. I'm just rewriting the function plus 4y. Okay, so let's move this now. Alright, so what's left? We did this guy and we did this guy, so we just have the x-axis. Okay, we just have the x-axis left. So 3 on the line segment AC. Okay, what's going on the line segment AC? Well, how can we say the line segment AC? Well, the line segment AC, that's just the x-axis. That's just y equals 0, right? The piece where y equals 0. So what does that imply? F of xy is the same thing as f of x0. So plug it in here. F of x0 is, well, it's going to be x squared. Wherever you see a y, these terms are gone. So it's x squared minus 2x. So in this case, setting the derivative equal to 0, okay, means we have 2x minus 2 is equal to 0. So from here, we'll get 2x minus 2. So we're going to get x is equal to, so implies f prime is 0 when if x is equal to 1. Okay. So x is equal to 1, but what the y value? Well, y value is 0. So here we get the point 1, 0. And let's calculate the z. 1 minus 2 is minus 1. So this is just minus 1. Okay. So this is the other candidate. Now what's left is these 3 points. So we checked everything in between. Okay, we checked everything in between. We got some kind of curves when we cut it this way, when we cut it this way. When we cut it this way, we got two-dimensional curves. And we took the derivatives. Now we just have to plug in the points A, B, C. Okay. Well, for A, at A, well, what is the x-coordinate of A? That's minus 2. What is the y-coordinates? That's 0. So just plug into the function again. Okay, let's plug it into the function. And we are going to get minus 2 squared is going to be 4. This is going to be 0. This is going to be, again, another 4, 8. And this is going to be 0. So that's just an 8. Okay. Okay, so we have minus 2, 0, 8. Now let's do B, number 5, at B. Okay, what do we have? What are the coordinates for that? Well, the x-coordinate is 2. The y-coordinate, well, I get it from this this line. The y-coordinate, x-coordinate is 2. Y-coordinate is going to be x at x equals 2. This is going to be 4. So 2, 4. Let's calculate the z-coordinate now. Let's plug into our equation. 2 squared, that's going to be 4. This is 16. Okay, so that's a minus 8. Minus another 4. That's a minus 12. Plus 16. So that's going to be a 4, I believe. Let me just check my work. No, where did I write this? At 2, 4. Hold on, it's supposed to be 0. Let's do it again. Let's plug into this function. We're going to have 4. 2 squared is 4. Minus a 16. That's a minus 8. Plus minus a 4. minus a 12, minus a 4, that's a minus 16, plus 16, yeah, that's a 0. Okay, so it's 240. That was my bad, I'm sorry. So we have the point 240. Okay, so finally, let's do as the 6th point, let's do at C what's going on. Let's see what's going on at C. Let's plug in C. Well, C is easy. It's going to be 2, instead of minus 20, we have 20 this one time. So go back and plug it into the function. We have 4. This is gone. Minus 4. Well, that's gone. That's gone. So it's 200. Okay. All right. So now we have everything. Okay. So we have to compare all of these points. So let's summarize these. Let's just summarize the whole problem. Summary. Let's put all the numbers together so you can see it. So so we had the interior point. We just had interior point. We had just one interior point, and from the interior point we got the point 1, 2, 3. Okay, so that's the point that we got. Okay, on AB. Okay, on AB we had nothing. We got no points from here. Okay, on BC I believe we got a point on BC. On BC we had we got which point? On BC. Oh, it's right over here. We got the point 224. It's right over here on the top of the page. Okay, we got the point 224. On AC, you see, and it's right over here also. On AC, we got the point 1, 1, 0, minus 1. Okay, and so next at A, we have minus 2, 0, 8. At B, we have 2, 4, 0. And at C, finally, we have 2, 0, 0. Okay? So we found the interior points, and note the rest of the whole thing is checking the boundary actually. Okay, so you get a whole bunch of points from the boundary. Now the thing that we're looking at here is the heights. Okay, which one is the most? This one is the most. So this is the absolute maximum. Okay, that's the 8th value. And I again look at the z values. Which one is least? This one is the least, so this is the absolute minimum. So they both happened on the boundary. Okay. So this was an interesting question. When you have so the it gets a lot worse when you have more variables. If you were talking about the function of 3 independent variables, so it's a 4-dimensional shape. You again look at the interior points, but this time it's not the region, is actually a volume. Okay, it's a 3-dimensional space. The inputs are 3-dimensional. It's 3 variables. So you have the interior points. Then the boundaries are going to be surfaces. Okay, so and then again you have to find where those surfaces are limited, and then check the curves on the surfaces, and finally check the endpoints. So it's doable. It's doable by hand. When you're doing this for 2 variables, when you get to have 3 variables, it becomes very, very long. But what you have to remember is, although the problem is very long, it's actually very easy. You just do the same thing for interior points. You find the where the derivative is equal to 0, find their z values, then you just plug in the boundaries, the curves on the boundaries, and simplify it down to a single variable equation. Take the derivatives, set them equal to 0, and find where they are maximums or minimums, where the critical points are. Then you have to check the points on the boundary itself. Okay, so we have three corners. You have to check the 3 corners. Okay, so that's about it. Maybe we'll do some more examples later on, but I want to add this. I want to end this section on local extrema and global extrema, absolute extrema. So hopefully I'll see you next time. Take care. Bye bye.